Okay, hi everyone, welcome back to this live stream. So in our previous video, I showed you how to do a setup for a Windows Server 2003 operating system. So now I want to continue on with Windows Server 2000 administration. Okay, for example, suppose you want to chop up a Class C network 200.211.192.x into two subnets. As you can see in the table, you'd use a subnet mask of 255.255.255.128 for each subnet. The first subnet would have a network number 200.211.192.0, router address 200.211.192.1, and broadcast address 200.211.192.127. You can assign IP addresses 200.211.192.2 through 200.211.192.126. That's 125 different IP addresses. Notice that heavily subnetting a network results in the loss of progressively greater percentage of addresses of the network number, broadcast address, and router tables. The second subnet will have network number 200.211.192.128, router address 200.211.192.129, and broadcast address 200.211.192.255. Now you may be wondering how you can subnet a Class C network, as in table 1.5. If you're using 2x minus 2 calculation, the subnet 128 in the table doesn't make sense. It turns out that there's a legitimate reason to do it this way. One, remember that using subnet 0 is not allowed according to RFCS, but by using it, you can subnet your Class C network with a subnet mask of 128. This uses only one bit, and according to your calculator, 1 minus 2 equals 0, giving you 0 subnets 2. By using a router that supports subnet 0, you can assign 1 minus 127 for hosts and 129 minus 254 for hosts as stated in the table. This saves a bunch of addresses. If you were to stick to the method defined by RFC standards, the best you could gain is a subnet mask of 192, 2 bits, which allows you only two subnets, 2 minus 2 equals 2. To determine the first subnet number, subtract the subnet mask from 256. Our example yields the following equation. 256 minus 192 equals 64. So 64 is your first subnet. To determine a second subnet number, add the first subnet number to itself. To determine a third subnet, add the first subnet number to the second subnet number. To determine a fourth subnet number, add the first subnet number to the third subnet number. Keep adding the first subnet in this fashion until you reach the actual subnet number. For example, 64 plus 64, 128. So your second subnet is 128. Add 128 plus 64 is 192, because 192 is the subnet mask. You cannot use it as an actual subnet. This means your valid subnets are 64 and 128. The numbers between the subnets are your valid hosts. For example, the following are valid hosts in a Class C network with a subnet mask of 192. The valid hosts for subnet 64 are in the range 65 minus 126, which gives you 62 hosts per subnet. Using 127 as a host would mean your host bits would be all ones. That's not allowed because that's all ones. format is reserved as the broadcast address for that subnet. The valid hosts for subnet 128 are in the range 129 minus 190. You might be asking yourself, what happened to 191 minus 254? Question mark. The subnet mask is 192, which you cannot use, and 191 would be all ones and used as the broadcast address for this subnet. Anything above 192 is also invalid for this subnet because these are automatically lost through the subnetting process. As you can see, this solution wastes a lot of addresses, 130 to be exact. In a Class C network, this would certainly be hard to justify. The 128-bit subnet is a much better solution if you only need 2 subnets. But what happens if you need 4 subnets in your Class C network? By using the calculation of 2x number of masked bits minus 2, you would need 3 bits to get 6 subnets. 3 minus 2 equals 6. What are the valid subnets and what are the valid hosts of each subnet? Let's figure it out. You're likely, okay, I can read that. I don't think I need to read that there. To figure out the valid subnets, subtract the subnet mask 256 minus 224 equals 32. So 32 is your first subnet. The other subnets will be 64, 96, 128, 160, and 192. The valid hosts are the numbers between the subnet numbers, except the numbers that equal all ones. These numbers will be 63, 95, 127, 159, 191, and 223. Remember that using all ones is reserved for the broadcast address of each subnet. The valid subnets and hosts are as follows. Subnet host 32, 32, 62, 64, 65, 94, 96, 97, 126, 128, 129, 158, 160, 161, 190, 192, 193, 222. You can add one more bit to the subnet mask just for fun. You were using 3 bits, which gave you 224. By adding the next bit, the mask now becomes 24011110000. By using 4 bits for the subnet mask, you get 14 subnets because 24 minus 2 equals 14. This subnet mask also gives you only 14 bits for the host addresses, or 14 hosts per subnet. As you can see, the amount of hosts per subnet gets reduced rather quickly when subnetting a Class C network. The first valid subnet for subnet 240.16, 256 minus 240 equals 16. Your subnets are then 16, 32, 48, 64, 80, 96, 112, 128, 114, 160, 176, 192, 208, and 224. Remember that you cannot use the actual subnet number as a valid subnet, so 240 isn't valid as a subnet number. The valid hosts are the numbers between the subnets except for the numbers that are all ones, the broadcast address for the subnet. The following are valid subnets and hosts: 16, 17, 30, 32, 33, 46, 48, 49, 62, 64, 65, 78, 80, 81, 94, 96, 97, 110, 112, 113, 126, 128, 129, 142, 144, 145, 158, 160, 161, 174, 176, 177, 190, 192, 193, 206, 208, 209, 222, 224, 225, 238, Class B. Because a Class B network has 16 bits for host addresses, you have plenty of available bits to play with when figuring out a subnet mask. Remember that you have to start with the leftmost bit and work toward the right. For example, a Class B network would look like x.y.0.0 with the default mask of 255.255.0.0. Using the default mask would give you one network with 65,564 hosts. The default mask in binary is 1111111 dot 111111 dot 0000000 dot 0000000 dot. The ones represent the network and the zeros represent the host. So when creating a subnet mask, the leftmost bits will be borrowed from the host bits, zeros not ones, to become the subnet mask. You use the remaining available bits for hosts. If you use only one bit, you have a mask of 255.255.128.0. This mask will be somewhat harder to subnet than the Class C 128 subnet mask. With 16 bits, you typically don't need to worry about a shortage of host IDs, so using 128 just isn't worth the trouble. The first mask you should use is 255.255.192.0 or 111111 dot 111111 dot 11000000 dot 0000000 dot. You now have three parts of the IP address: the network address, the subnet address, and the host address. A 192 mask is figured out the same way as a Class C network address, but this time you'll end up with a lot more hosts. There are two subnets because 2 minus 2 equals 2, or that probably should be 2 to the power 2, I think. The valid subnets are 64, 128, 256 minus 192 equals 64, and 64 plus 64 equals 128. However, there are 14 bits, zeros left over for host addressing. This gives you 16382 hosts for subnet 2 to the power 14 minus 2 equals 16382. The valid subnets and hosts are as follows: subnet host 64x.y.64.1 through x.y.127.254, 128x.y.128.1 through x.y.191.254. You can add another bit to the subnet mask, making it 111111 dot 111111 dot 11100000 dot 0000000 or 255.255.224.0. There are 6 subnets: 2 to the power 3 minus 2 equals 6. The valid subnets are 32, 64, 96, 128, 160, and 192. 256 minus 224 equals 32. The valid hosts are listed here: 32 x.y.32.1 through 63.254, 64 x.y.64.1 through 95.254, 96 x.y 96.1 through 127.254, 128 x.y 128.1 through 159.254, 160 x.y 160.1 through 191.254, 192 x.y 192.1 through 223.254. Therefore, if you use a 2 255.255.224.0 subnet mask, you can create 6 subnets, each with 8190 hosts. You can add a few more bits to the subnet mask and see what happens. If you use 9 bits for the mask, it gives you 510 subnets. 2 there to the power 9 minus 2 equals 510 with only 7 bits for hosts. You still have 126 hosts per subnet. 2 there to the power 7 minus 2 equals 126. The mask looks like this: 1 1 1 1 1 1 1 1 dot 1 1 1 1 1 1 1 1 dot 1 1 1 1 1 1 1 1 dot 1 0 0 0 0 0 0 0, or 255.255.255.128. You could add even more bits to see what you get. If you use 14 bits for the subnet mask, you get 16382 subnets. 2 there to the power 14 minus 2 equals 16382, but this gives you only 2 hosts per subnet. 2 there to the 2 to the power 2 minus 2 equals 2. 1 1 1 1 1 1 1 1 dot 1 1 1 1 1 1 1 1 dot 1 1 1 1 1 1 1 1 dot 1 1 1 1 1100, or 255.255.255.252. You may be wondering, why would you ever use a 14-bit subnet mask with a Class B address? This approach is actually very common. Think about having a Class B network and using a subnet mask of 255.255.255.0. You would have 254 subnets and 254 hosts per subnet. Imagine also that you have a network with many WAN links. Typically, you'd have a direct connection between each site. Each of those links must be on its own subnet or network. There will be 2 hosts on these subnets, one address for each router port. If you used the mask described earlier, 255.255.255.0, you would waste 252 host address per subnet using the 255.255.255.252 subnet mask. You have many subnets available, each with only 2 hosts. You can use this approach only if you are running a routing algorithm like Enhanced Interior Gateway Routing Protocol, EIGRP, or Open Shortest Path First, OSPF, which we will talk more about later in this book. These routing protocols allow what is called variable length subnet masks, VLSMS. VLSM allows you to run the 255.255.255.252 subnet mask on your interfaces to the WANs and run 255.255.255.0 on your router interfaces in your LAN. It works because routing protocols like EIGRP and OSPF transmit the subnet mask information in the update packets that it sends to other routers. Or IP doesn't transmit the subnet mask and therefore cannot use VLSM. So I'm going to leave it here today for this video. Thank you for listening, and I hope you have a nice week. Thank you.